Okay, then welcome everybody to our first intercontinental seminar talk of the Intercontinental Seminar Series on Gravity and Cosmology. First of all, thank you very much for subscribing. We have a lot of subscribers, and to be honest, I didn't expect to reach that number so fast. Before we start, before I introduce our today's speaker, one short request. I already said it before, please turn your camera off during the talk. And also, Nico and I talked about how to arrange it with the questions during the talk. So please ask questions which are immediate for the understanding of the talk during the talk, and more extending questions later after the talk. So, let me come to our today's speaker. Our today's speaker is Domenico Giulini. He did his PhD in 1990 at the University of Cambridge, and then he made his habilitation and Linear Legendi in 1996 at the University of Freiburg. And now he is a professor at the Leibniz University of Hannover, and he is also in a collaboration agreement with the ZARM at the University of Bremen. And his main work covers general relativity and also quantum physics. And today he will talk to us about basically the early history of general relativity. And his talk will be basically hiking in pathless terrain, the genres of GR. And with that, I hand over to you, Nico. Thank you very much for giving this talk to us today.
Yes, thank you for the introduction, and thank the organizers for this meeting, for the invitation to this meeting. I feel pleased and honored to speak to such a wide audience. In our early discussions on what I could talk about, we agreed that perhaps for the first talk in the series, some history would be appropriate. So you can lean back. It's basically a non-technical talk with some technicalities being distributed throughout the talk. And the talk is basically divided into three parts, as you can see on the right-hand column. So essential steps means essential steps in the conception of GR. I will tell you about some of the aspects that you might not know. I've chosen the topics according to my guess what is known and what is not known. Then I will talk a little bit about some technical points, also relating to early ideas about what a quantum theory of gravity could do. And then I will talk about other contributors to the development of GR, in particular about Hilbert and Weyl, two mathematicians who made major contributions to general relativity, some of which are well known and some of which are not so well known, and some of which are sort of usually reported in a way that is, in my opinion, not quite accurate. Okay, so let me start. In 1955, there was a conference in Bern celebrating 50 years of special relativity, and Einstein was invited to this conference to come back to the city where he sort of intellectually grew up. But unfortunately, he died early this year. And so Max Born gave a lecture, partly replacing him, in which he said the following: retrospectively, the formulation of the general theory of relativity appeared to me then, and still appears to me today, as the greatest achievement of human thought about nature, the most astonishing union of philosophical depth, physical intuition, and mathematical artistry. But at the time, it had little connection with empirical facts. It attracted me like a piece of art that one delights in and admires from a considerable distance. And this, I think, describes very well the early history of GR, because it was considered to be mathematically complicated and physically not very telling. And that, of course, changed in the 1950s and 60s, but up to then, that statement is basically true. Einstein formulated his theory in 1915, finished the formulation in 1915, as we will see. In the 1916, in January, just after finishing it, he wrote to his dear friend, Hendrik Anton Lorentz, whom he admired very much, in a letter the following: the series of my papers on gravity is a chain of errors, yet gradually leading closer to the goal. Therefore, the basic formulas are finally okay, but the derivations are abominable. This deficiency still needs to be rectified. So he considers the derivation to be terrible. And he hoped to come back to this and to sort of rectify that. Yet further on, in a famous lecture in 1933, in the so-called Gibson lecture, which we will talk about later also, he made a very impressive statement about the feeling he had during the time when he conceived GR. And he said the following in this lecture: once the validity of this mode of thought has been recognized, the final results appear most simple. Any intelligent undergraduate can understand them without much trouble. But the years of searching in the dark for a truth that one feels but cannot express, the intense desire and the alteration of confidence and misgiving until one breaks through to clarity and understanding, are only known to those who have had the experience for themselves. And this is why I call this talk Hiking in Pathless Terrain, because if you have ever been in the mountains, and if you head to areas of mountains where there are no signposts and paths for tourists anymore, you will know that it is infinitely more difficult to go on the same mountain with or without these signposts and these tourist paths. And I always considered the search for GR as sort of hiking in the path in the mountains without a sort of fixed trail that has signposts in it and gives you assurance that you are on the right track. If you're not assured, then the psychological uncertainty is a very strong feeling. Okay, so the essential steps between special and general relativity, of course, go between the 10 years between 1905 and 1915. And of course, it starts with special relativity, slightly later the equality between inertial mass and energy. In 1907, Einstein made a very nice thought experiment that the stress under which a body is put actually contributes to its inertia and possibly its gravitational force. And we will see this thought experiment later on. In 1911, he made a prediction of light reflection just on the basis of the equivalence principle, which he got wrong by a factor of 1/2, but which nevertheless led to the attempt to test this by solar eclipse in Russia. And this expedition was cancelled because of the outbreak of the First World War. In 1912, Einstein considered a linear theory, a nonlinear theory of scalar gravity that I also will talk about, which gives rise to an interesting equation, as you will see, which is still of some interest today. And he made an argument that there is an effect that is close to electric induction, an analog of electric induction, and that may explain the inertial mass as due to the interaction with all other masses, an idea which is usually referred to as Mach's principle. Mach had the idea that the inertia of a body, the mass, has to do with the interaction with other bodies. In 1913, he wrote with his dear friend Marcel Grossmann a so-called Entwurf theory, a conception theory, which brought him very close to GR. And in that paper, he gave an argument why the general equations cannot be generally covariant, an argument which was erroneous and which cost him 2 more years until he sort of came back to general covariance 2 years later. In a notebook that has been found and has been sort of described by scholars on history of physics very, very accurately, the so-called Zurich notebook, we can follow his lines of thought and can follow how he actually got the idea that in the end, everything must be formulated in terms of differential geometry. And then in 1915, there were 4 papers, all written in November, within 20 days, within 3 weeks, on the 4th, on the 11th, on the 18th, and the 25th of November, containing the last paper contains the final field equation. And also the correct, subsequently the calculation of the perihelion shift of Mercury. On November 20th, in 1915, and later in 1917, David Hilbert, the mathematician from Göttingen, submitted 2 papers called The Foundations of Physics. And these papers also contain the right field equations. And what is interesting is that Hilbert's paper was submitted 5 days earlier than Einstein's. So Einstein's was on 25th and Hilbert's was on 20th. And that gives rise to people now saying that Hilbert was the first to find the right field equations, and Einstein was slightly later. And I will have to say more about this later. And then in 1918, I want to mention that Hermann Weyl, the mathematician, also in Göttingen, and then later in Zurich, wrote the first systematic textbook on GR called Raumzeit Materie in German, which means space, time, and matter. And that book has undergone 5 editions in the subsequent 5 years. It's a very impressive book, and if you don't have it, you should read it. It's very nice. And this, just as a curiosity, in 2010, there was an auction at Christie's, the auction house, where they sold Einstein's Gibson lecture. And I found this by accident. And it was, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8 pages, handwritten notes of Einstein of this Gibson lecture in 1933, of which I already read some part. And they estimated they could make $250,000 to $350,000, but in fact they made almost 600,000. So somebody bought it at $600,000, just as a curiosity. And I want to read something from this lecture to you, because that makes understandable how Einstein actually found his path to GR. So this is all quotes, what I'm reading now. So he said, the most obvious procedure would have been to retain Laplace's scalar potential, meaning the gravitational potential, and to amend Poisson's equation by a term including time derivatives in the obvious way, we will see what this means, so as to comply with special relativity. In addition, the law of motion of a mass point had to be adapted. Such investigations led to a result that aroused my deepest suspicion. Namely, according to classical mechanics, the vertical acceleration suffered by a body in a vertical gravitational field turns out to be independent of the body's horizontal velocity component. That's the statement about what Einstein thinks is known from experiment. It follows from this that the vertical acceleration of a mechanical system in such a field should be independent of its internal kinetic energy. But according to the theory I was investigating, the vertical acceleration was not independent of the horizontal velocity and consequently not independent of the internal energy of a system. This did not agree with the old, well-known empirical result that all bodies in a gravitational field are subject to the same acceleration. This principle, which can also be stated as the law of the equivalence of the inertial and gravitational mass, impressed me as being of fundamental importance. I wondered how this law could exist and believed that it held the key to real understanding of inertia and gravitation. I never seriously doubted its exact validity, even though I did not know about the beautiful experiments of Erdős, which, if I remember correctly, were not known to me until a later date. So what is he saying? He's saying you take the well-known equation of gravity in the Newtonian theory, where the plus phi equals up to a constant, the mass density. And if you want to make it special relativistically invariant, it means invariant under the Poincare group, you replace the Laplace operator by the wave operator and the right-hand side by a scalar. Now the scalar, the only scalar you can build is not, of course, the energy density, because the energy density is the 0,0 component of the energy momentum tensor. So you must take the trace, an idea which was told by Einstein by von Laue. So that would be the obvious generalization of a scalar theory of gravity. The obvious generalization of the equation of motion from Newtonian physics would be to replace the second derivative of the spatial position by the second derivative with respect to proper time of the four-dimensional position in space-time. But these are four components, and these are just three components. So unless you put a projector on the right-hand side, you have too much information. You see, the left-hand side is the forward acceleration. The forward acceleration is always perpendicular to the forward velocity. So if you don't put the projection perpendicular to the forward velocity on the right-hand side, you get an equation whose integrability condition is saying that you can only integrate this equation if the gravitational potential does not change along the world line. In order to not get this, this additional requirement, you put a projection operator on the right-hand side, which makes the right-hand side also perpendicular to the forward velocity, like the left-hand side. So that would be the obvious guess. And that equation can be discussed. Some time ago, I had some paper on this, investigating what is really wrong and what is not wrong with the scalar theory of gravity, because that's sometimes, I think, not quite correctly stated in the literature. Okay, so this, I think, is basically what Einstein had in mind. There is no notes from Einstein of that time, except for that statement in the Gibson lecture. Now, if you do this, you can actually boil down all the equations of motion to that equation, to that sort of changed Newtonian equation, where the second derivative with respect to coordinate time equals the gradient of the gravitational field, but then multiplied with a factor 1 minus beta squared, where beta is v over c. And that is precisely what Einstein was saying. He says that the velocity depends on the internal energy, the acceleration depends on the internal energy. This is what he means by it did not agree with the old well-known empirical result. Namely, if you drop something from a tower, then the way the amount, the vertical amount it has fallen through depends on whether you have a initial horizontal velocity. If you have a great initial horizontal velocity, the amount of distance it has fallen through decreases with increasing horizontal velocity, like sort of depicted in this funny picture. But the invariant statement would have been, you should not compare the amount by which it has fallen according to coordinate time, but according to proper time. And if you calculate this in terms of the proper time, if you really want to test the equivalence principle in a meaningful way, then you would ask how much vertical distance a body has fallen through for equal proper time, not for equal coordinate time. And if you calculate that, then you find, in fact, if you replace coordinate time by proper time, then there is the fulfillment that the time it takes for a body to have fallen through a distance h, the proper time, is a function that depends only on h and the gravitational acceleration. It does not depend on the initial horizontal velocity. Unlike the coordinate time, that depends on the gamma factor, and the gamma factor being 1 over square root minus 1 minus beta squared. So for a fixed distance, it takes more coordinate time to fall through if the body had an initial horizontal velocity. And that apparently seems to have been what Einstein calculated. But if he had calculated in terms of invariance, he would have found a full satisfaction with the requirements of what he called the equivalence principle. However, the scalar theory of gravity has also other deficiencies, one of them being it gives the wrong perihelion shift. It gives minus 1/6 of the value that general relativity predicts. So it has the wrong shift. And it also gives no bending of light, of course. So these things are of course, wrong with scalar gravity, but it does not, in a proper sense, violate the equivalence principle. Then there is Einstein's other argument in 1907 that stresses contribute to weight. And he has a very nice thought experiment. He considers a rigid rod moving at constant velocity relative to a coordinate frame that he calls K. And then he thinks that a co-moving observer in the rest frame of the rod applies simultaneously forces on the trailing end and on the leading end of equal and opposite strength. So you take the rod, and in your rest frame, which is the rest frame of the rod, and you apply a force at the back and at the front, simultaneously of equal magnitude, then of course the rod will not move because you apply them simultaneously and of equal magnitude. The only thing you change is the stress within the rod. But as seen from an observer against which the rod is moving, the stresses will not be applied simultaneously. The trailing end receives the force earlier than the leading end. And you can calculate the time difference depending on the velocity of the rod. And then you can ask, how does the observer against whom the rod is moving, how does he judge the situation? And he would say the rod receives a pushing force before he receives the counterforce. But the velocity of the rod is not changing. Since it isn't changing in its rest frame, it is not changing in the other frame. The velocity is non-zero, but it doesn't change. So the rod receives a force in the forward direction before it receives the counteracting force, which has not the effect of enhancing its velocity. And since there is a net momentum transfer, this means that the mass must have increased in order to fulfill the conservation of momentum. And now you can calculate how much mass the body receives through the process of applying stresses. And then he calculates the amount, and the amount is the stress within the body times the volume divided by c squared. And that was the first hint that a body under stress has a different inertial mass and probably a different gravitational mass than a body without stress. And that is, of course, found in GR. And if you remember in GR, the so-called Tolman-Oppenheimer-Volkoff equation, that is the equation that rules the negative gradient of the pressure as you move inside the star, then it has three terms which would also exist in Newtonian physics, and the relativistic corrections are written here in red. And all these corrections go with 1 over c squared. And these corrections have, two of these corrections have an explanation which just relate to what I have just said. Namely, the active gravitational mass, the passive gravitational mass, are enhanced by the body being put under stress. So so to speak, the gravitational field gets bigger of a body that's put under stress. So that means the active gravitational mass is bigger. But also a body that is put in a fixed gravitational field, if you put it under stress, is sort of attracted stronger than a body, the same body with the same number of baryons, but not put under stress. It has less weight. And that is the reason for gravitational instability of stars in GR. Because in Newtonian physics, if you have an effective mechanism that produces a pressure to counterbalance the weight of the atmosphere of the star, then you can always sort of increase the pressure so as to stabilize the star. But in GR, that's not possible. Because once there is a competition between building up stresses in order to not let the body collapse, and the effect that building up stresses increases the weight. And there is a point beyond which you cannot stabilize the body by increasing the pressure, because then the weight just gets so much bigger, then you will never be able to balance this. And this gives rise to instabilities, as we know, and gravitational collapse. And one of the statements is the so-called Buchdahl limits. That means that if you have a body of mass m, then you cannot compress it further than the limit, which is 9/8 of the Schwarzschild radius. Otherwise, the pressure becomes infinite. And you get an even stronger bound if you put conditions like, okay, the pressure may be finite in the inside, but the velocity of sound gets larger than the velocity of light. So you get this typical lower bounds for the radius of a body given its mass. And that's an effect that shows that is related to Einstein's very early thought experiment. And that paper of 1907 is very nice. Then Einstein was sort of occupied with different things. And in 1912, he came back to the problem of gravitation at a time when he was moving to Prague in Czechoslovakia. And he had a short period there as a professor. And he invented different sort of ideas about implementing the equivalence principle such that gravitation and acceleration is somehow the sort of similar, and he sort of played around with certain equations. And that's the first equation he came up with. And you should read C. It has the meaning of the velocity of light, but you should read C as the gravitational potential. And this looks very much like the Poisson equation, but not quite, because there's a C on the right-hand side. So this equation is truly linear, whereas the Poisson equation is linear inhomogeneously. It has only rho on the right-hand side and no C. So he came up with this equation and said that this is a possible replacement of the gravitational field equation. But slightly later, he sort of modified this and came up with a slight modification, which is this equation, which has this additional term. And that term accounts for the fact that the energy that is stored in the gravitational field is itself a source of gravity. So gravity gravitates, right? So there is a self-effect that gravity sort of enhances its own strength or diminishes depending on the sign. And this is a nonlinear equation. And what is interesting about this equation is you find it literally in GR again, if you consider the 0-0 component of Einstein's equations for static spacetimes. You can put this in, and if you identify the quantities correctly, you can find this equation again in as one component, namely the time-time component of Einstein's equations. And that are once outlined in a paper. In fact, you can derive this equation by a very nice sort of line of thought from from Newtonian physics, by implementing the idea that the energy that is stored in the gravitational field should be itself a source of the gravitational potential. And if you follow that thought, then you can derive a consistent equation that satisfies this condition, which is precisely this equation. Einstein made it differently, but that would be also a way to arrive at this nonlinear scalar field equation. Let me say that as nice as the equation is, of course, it gives also the wrong perihelion shift, right? So it's experimentally falsified. But theoretically, it is a consistent equation. Shortly after that, he returned to Zurich, and he wrote the sort of conception theory, the Entwurf theory, with his friend Marcel Grossmann. And that's sort of the first page, 1913. And Marcel Grossmann wrote the mathematical part. And Einstein wrote the physical part here, the physikalische Teil, the physical part. And in that paper, which is fairly long, they almost got to the GR, but then at the end, they took the wrong turn, apparently being able to argue that GR, or the gravitation theory, cannot be a generally covariant theory. We can talk about this later. That's an interesting argument, but it takes some time to explain it. They also came up with an argument why gravity cannot be described by a scalar theory. And they did not give the argument that it gives the wrong perihelion motion. They didn't even calculate the perihelion motion for the scalar theory. They gave a different argument. And that argument is immensely interesting and telling because the argument in the end is wrong. And from wrong arguments, you usually learn a lot. And he gave the argument that Einstein gave the argument that such a theory, a scalar theory of gravity, which is in the context of special relativity, necessarily violates energy conservation. And for a modern reader, this sounds absurd. Because if you have a Poincare invariant theory of anything, then of course, by the mere fact that it is Poincare invariant, we know from Noether's theorem that there is a conserved quantity associated to time translation symmetry, which we would call energy, and that is conserved. So somehow Einstein had an idea what energy should be, which is different from what Noether's theorem gives you. And he argued that his kind of energy is not conserved. And the argument is about a radiation being put in a box, and then you lower the box filled with radiation in a gravitational field. Then you release the radiation and you pull up the box again, and you guide the radiation back up to the place where it started from. And then because of redshift, you can argue that there is a net win of energy. And the mistake in that argument is that Einstein did not take into account that the stresses that the radiation-filled box has in its walls contributes to the weight. Something he should have known, because in 1907 he derived it himself. And if you go through this argument, you can show that this argument just comes out right, namely that energy is conserved, if you take into account the fact that a box with radiation in it has a different weight, not only because of the radiation, but it also has a different weight because the radiation exerts some pressure on the walls, and the walls would increase in their weight because of the pressure. And that's neglected in that argument. But Einstein thought this argument is convincing, and he said that it can't be a scalar theory of gravity. And that was important at the time because there was a competing theory of gravity by Gunnar Nordström, the same Nordström as in Reissner-Nordström solution. And he had a scalar theory of gravity, which was competing with Einstein's theory, or Einstein's theories, and Gunnar Nordström got it very far with his ideas, and many people actually favored his theory. For example, Max von Laue. He wrote even a paper about it. Okay. Now here is the Zurich notebook that I promised you. It's hard to read, and the only thing I want to show you are 2 pages. And what Einstein tests on these 2 pages is whether his field theory satisfies the condition that the apparent gravitational field that you get by pure acceleration satisfies his equations. So on the left-hand side, he makes a simple and very elementary calculation. What is the acceleration field that you feel if you transform yourself into a rotating coordinate system in a rotating reference frame? And then he checks whether the apparent velocity, the acceleration field, satisfied what he considered at that time to be the right field equation. And then he has, let me just focus, and then he says somewhere, stimmt, that means it's correct. And that is where he tests that. So he tests whether an acceleration field could be considered to be a gravitational field. And then sometimes, some pages later, written at a later time, you suddenly discover that the symbols change. And the symbols are now the symbols of differential geometry. And let me again focus in. What you see in the first line is the definition of the Ricci tensor. The Ricci tensor written in the old-fashioned form where the Christoffel symbols are written with these curly brackets. And above that line, you see the name Grossman. He writes Grossman. And it was Grossman who told him that differential geometry provides a quantity which could be the left-hand side of his equations. He knew that the right-hand side has something to do with the energy-momentum tensor, but the energy-momentum tensor, if it is not contracted, if it's not taking the trace off, if it's not the scalar, then it must be just the tensor. But what could be on the left-hand side, he asked. And Grossman said, well, on the left-hand side, there could be something like the Ricci tensor. And this is sort of the appearance of Grossman, who told him that. And then he makes lots of calculations with this tensor and discovers some of its quantities, its properties, and so on. So we can very closely follow how Einstein's thoughts developed from very simple models of gravity with acceleration fields to the final equation. And then in 1915, he came to his oops, sorry. He came to his 4 papers in three weeks. And this is the last one. I just want to show you that it contains the right field equation here under, here where my cursor is, right-hand side in the middle, 2a. That's the right field equations as you know it. G for Einstein is the Ricci tensor, not the Einstein tensor. And on the right-hand side is the trace inversed energy momentum tensor. So that's just the way we would write the equations. And then that paper is only 4 pages long. That's the second part of it. And then he says here that that gives you the final theory of gravity. And so that was his final word on GR and the final formulation with the right field equations. So if we just compare what has been done, we start from Newtonian equations and we get by Einstein's equations. What's the major difference? Instead of 1 potential, we have 10 potentials. In 1 equation turns to 10 equations. The equations of motion in Newtonian way get changed to this, but it's not only a change of equations, it's also a change of meaning. Because in Newtonian physics, you have a God-given inertial structure. Namely, you know what force-free motion is before you solve any equations. And then gravity is a force in the sense that it causes deviations from inertial motion. But in Einstein's theory, the metric is necessary in order to determine what inertial structure is. So the equation of motion is the motion of a force-free body. And that means gravity ceases to be a force in the Newtonian sense. It's part of the inertial structure. So there's a different meaning also in these equations, which will become important later on. Okay, and this is just the sources of gravity is not just the energy density as said above, but there's also the energy current density, the momentum density, and the momentum current density. They all give sources to gravity fields. And sometimes you can parameterize like this. Then you have the scalar, sort of the Newtonian-like part of Einstein gravity. You have the gravitomagnetic part, and you have the gravitational wave part. All of them are sourced by these 10 quantities on the right-hand side, which summarize the energy momentum distribution. Okay, let me come back, sort of relating this to more modern things, to Einstein's early papers. In 1916, in half a year after he published the right field equations for the first time, he gave a theory of the linearized gravitational field. And he calculated he predicted gravitational waves, and he calculated the quadrupole formula. He got it wrong by a slight mistake, which he corrected 2 years later. But essentially, he has the quadrupole formula, and he says there must be gravitational waves. And he also predicted correctly that they had 2 polarization degrees of freedom by imposing what we now call the de Donder gauge or the Hilbert gauge. And in fact, I personally think that this is a misnomer because Einstein had it before Hilbert and de Donder. Hilbert even refers to Einstein's paper explicitly in writing down this gauge. And de Donder then generalized this to the nonlinear case, which is now called harmonic gauge. Anyway, but Einstein had it in 1916. And the interesting thing is, after he wrote down the quadrupole formula for the emission of gravitational wave, the power outlet of gravitational waves, he observed that the prefactor of this quadrupole triple dot square term is g over c to the 5th. And that's, of course, it's a term, it has units, but it's very small, right? G, the gravitational constant, is 10 to the minus 11. And c to the 5th is a very small number in standard SI units. So this is very small. So Einstein says literally that the energy loss due to gravitational radiation has a practically vanishing value in all imaginable cases. And immediately after he says that, he ends his paper with the following sentence, which is interesting. He says, due to the electron movement occurring within the atoms, atoms must emit not only electromagnetic, but also gravitational energy, albeit by a tiny amount. Since this should not actually occur in nature, because atoms are stable, it appears that quantum theory will have to modify not only Maxwell's electrodynamics, but also the new theory of gravitation. So half a year after he formulated his theory, he already sort of opened his eyes towards the possibility that the quantum theory, which in 1918 had not been yet formulated, but had been sort of anticipated that some change is going to be there in the future, he immediately said that quantum theory is doing to my theory of gravity the same thing as it will do to Maxwellian electrodynamics. So I think this was very, very wise. But this is a typical Einstein's argument, right? It's an argument of principle, not of practical importance. And Einstein didn't care very much about numbers, as we had seen above, because of this, when he first sort of dismissed the scalar theory of gravity because of inhibited vertical acceleration due to horizontal movement, which was not quite accurate. This argument, again, is in a sense outrageous, because you can calculate, in modern quantum theory, you can calculate the perturbation that a quadrupole perturbation of a gravitational field does to a hydrogen atom in first order of perturbation theory. This has been done by Weinberg in his book in 1971. That contains a mistake, but it has been corrected by Straumann some years later. And the result is this, that you have a mean lifetime of 10 to the 31 years. So that's the decay rate of a quadrupole transition of 3d to 1s in the hydrogen atom being caused in first order perturbation theory by the quadrupole perturbation. And that means that the mean lifetime of a hydrogen atom against that kind of spontaneous emission is 10 to the 31 years, which is 10 to the 21 times the age of the universe. So that's pretty stable. And Einstein said, without doing any kind of calculation, and you could have done a pre-quantum theory correspondence principle-like argument that gives you the right number, up to a factor of 10 perhaps, at the time of Einstein. But Einstein didn't care. He was not into numbers, he was into principles. And likewise, Freeman Dyson, later in 2012, estimated, for example, graviton absorption rate to the Earth. And he, for example, he estimated that you will have 4 solar gravitons being absorbed by the whole of the Earth in 5 million years. And that the detection of a single graviton by a laser interferometer of current design would mean to detect length changes of about the order of the Planck length. So the notion of a graviton and its emission and absorption rates is, of course, very, very far from whatever we can hope to test. But Einstein in 1916 took this argument seriously. And another point I want to raise, which is not so much geared to Einstein's thinking, but it's of interest for us, and it's a very nice argument. There has been a hope that if you include the concept of quantization to the theory of if you sort of expose the gravitational field to quantization, whether it's being phenomenologically relevant or not, as a matter of principle, there is the hope that it could cure the problems that we have with current quantum field theories. And here is a very, very simple argument why that hope might not be altogether desperate. And you might have seen that argument. I don't know who first invented this. I learned it from Norbert Straumann, but it's a general argument. Consider a spherical shell of radius r that has some rest mass m0 and a gravitational mass mg. Then in Newtonian or semi-Newtonian physics, you would say that the energy of that is its rest energy, And the shell is also charged. You give it a charge, which is uniformly distributed over the shell. So then the total energy is made up of the rest mass. It's made of the electrostatic self-energy, which is Q squared over 2R. And it's also made up of all the energy stored in the gravitational field, which according to Newton's theory is negative because gravity attracts, right? You win energy if you bring things together. So that is negative. Now, the interesting question is, what is the m that is squared on the right-hand side? What m do you take as that m that gravitates? Well, if you naively say the rest energy, then of course you get divergences if r goes to 0. But now let's take a different m. Let's say the total energy is, of course, the inertial mass times c squared according to special relativity. I'm not being quite consistent here because I'm mixing up principles from special relativity and Newtonian gravity. I know that, but I want to make the argument as simple as possible. So I do this for the moment. So say the total energy is the inertial mass times c squared, and then add on top of that the principle that the gravitational energy is equal to the inertial mass. The gravitational mass is equal to the inertial mass. Then in that equation, there's only the E and the mg become the same up to a factor of c squared. And then this equation for E becomes a quadratic equation because that mg on the right-hand side is proportional to E. To E squared, or if you express it in terms of mg, you get a quadratic equation for mg. And mg is equal to the inertial mass, and we call that mass just m. The rest mass is still there, but the other masses are equal. And now you see you have a quadratic equation for m, which sort of incorporates the thought that all energies, may they be of rest mass nature, may they be of electromagnetic origin, or may they be of gravitational origin, and that's the last one is the important one, all energies gravitate. And the interesting thing, of course, is that this term comes with a negative sign, the m squared term. And now you have a quadratic equation for m, which you can solve. So, and here's its solution. You solve this and you get an energy contribution that depends on the radius of the shell, its charge, and its rest mass. And the interesting thing about that equation is that it has a continuous limit as r goes to 0. You can shrink the particle with a fixed mass, with a fixed charge to 0 size, and you do not get an infinite answer. You get a finite answer. Of course, the answer is compared to current elementary particles is outrageous, is proportional to the Planck length, times the charge measured in units of the elementary charge times the square root of 2 times the fine structure constant. But this is what you get. You get a finite answer. And this result you should compare to a power series expansion in terms of G. If you make a power series expansion in terms of the gravitation coupling constant, you get a divergence at each order. And this is because the limit G goes to 0 and the limit R goes to 0 are not uniform in each other, right? So you may not interchange these two limits. But if you don't care about this, you could get the impression, if you look at perturbation theory, that theory is perturbatively sick. But in fact, it is not. It has a finite value. And so the hope is that if we include gravity in our quantum field theory settings, all the divergences that we may encounter, for example, in calculating the self-energy of the electron, may go away if gravity acts in this full linear way, reducing all the energies to a finite size. That is a hope that has been around for a long time, and is not, I would say, altogether dead. And just to mention this at this point. Okay, so that brings me to the last part, discussing some of the other contributors. And first start with Hilbert. Now, Hilbert wrote his final paper in 1915 and submitted it to the journal 5 days before Einstein did. And since Hilbert's published paper has the right field equation, people usually say that Hilbert was the first one to write down the right field equation. But Hilbert's paper as it appeared in print is not identical to the paper that Hilbert submitted. Hilbert submitted the paper on the 20th of November, but the printed version is the one, the proofs of which you can see on the left-hand side. And if you look on the left-hand side, the date of the printer is the 6th of December. That has been found in the library in Göttingen a few years ago. And the story is that Hilbert changed his first submission, and he also changed the field equation that the original version had. But that change was not acknowledged in the printed version, so as to make it appear deliberately or not. I'm not accusing anyone of anything. It's just, this is how the story goes. And there was no acknowledgement, so making people think that what had been published is what had been submitted on the 20th of November. But that's not true, which is now known. And that's written down here. So later it was Corey, Wren, and Stachel, historians of science, that found this submitted printer's version, and that the November 20th version did not contain the right field equation. The story is that Einstein visited Hilbert in June of 1915 in Göttingen, giving several talks and private conversations about his theory, and got Hilbert interested in this. And so Hilbert himself thought about mathematical aspects of general relativity and worked out some things, including field equations and variational principles and so on, but maintaining for some time that the field equations cannot be generally covariant. And that was changed between November 20th and the 6th of December. And that is now understood. Anyway, so besides that, Hilbert made very valuable contributions, no question about this. He gave the first derivation from an action principle. He formulated conservation laws, or said how conservation laws could be obtained in GR, applying what has later become known as Noether's theorems, which were discussed in Göttingen at the time between Hilbert, Felix Klein, and Emmy Noether. He discussed quite extensively time-like and null geodesic in the exterior Schwarzschild solution, and emphasized the mathematical and physical role of so-called second Noether identities. His papers have the strange title, The Foundations of Physics. And he really means all of physics. He does not mean just gravity, he means all of physics. And he had the idea that perhaps physics would be almost sort of done with because of GR and a nonlinear theory of electromagnetism, which at the time was quite popular, having been formulated by Gustav Mie, an actual experimental physicist who had some strong theoretical ideas and also the knowledge to formulate them, and who gave the first form of nonlinear electrodynamics in which the field equations are nonlinear and in which there is no such thing as a charge distribution and currents as separate entities. It's only fields and their dynamics. And what we call charge and current are particular regions in space in which the electric and magnetic fields have particular properties. So reduced anything to nonlinear field equations of E and B and nothing else. And Hilbert was very much attracted by this, as was later Hermann Weyl. Now let me just go through this a little bit. So the Hilbert action, you know, if you have heard GR. But the Hilbert action, as you also might know, has to be amended by some boundary terms in order to give it actually a proper value and make it mathematically feasible, because without the boundary terms, it's actually not a differentiable function on those configurations that you like to include, like, for example, Schwarzschild. So you have to have some boundary terms. Hilbert did not have the boundary terms. Einstein had them later. And the boundary terms are chosen in such a way, so if you write down the Ricci scalar, then you will see that it has second derivatives, but the second derivatives occur linearly. So that means you can combine the second derivative terms in a total divergence plus a term that has only first derivatives. And now in the variational procedure, the boundary term doesn't contribute, so the second derivatives drop out. And that is the reason why the field equations are of second order, even though the Lagrangian density is also of second order. You would naively expect a fourth order differential equation from that. And then the important thing is that what remains after subtracting the boundary term is the right Lagrangian density, which is not a scalar. Right? It is a gamma gamma minus gamma gamma term, which in fact is just the gamma gamma minus gamma gamma term that is already in the Ricci scalar, but with a reversed sign by subtracting this. And Einstein was the first one who wrote down this Lagrangian density. It was later called after Hawking, Perry, York, Gibbons, somebody else rather, but it's Einstein wrote it down in a footnote, in fact, in one of his papers. And the important thing about this relation, that this right Lagrangian density is modulo a divergence, the same as a scalar, means that the action is diffeomorphism invariant, which means that if you write down the action, that has two arguments, namely the domain you integrate over and the field you are using in the Lagrange density, is such that if you transform the domain and the field by diffeomorphism, you get the same number. And that's true for any diffeomorphism. In particular, if the diffeomorphism is such that it is constrained to the inner region of the domain omega, that means it is the identity on the domain and outside the domain, then you find that the action is invariant under just transforming the field G. So you take a metric field, you calculate its action on a domain omega, and then you take a diffeomorphism transformed field, and you make the same computation with the transformed field over the same domain, and you get the same number. And from that relation, there follow interesting identities. And Hilbert, in his paper, had what I call an outrageous theorem. He had the theorem that says that the laws of electrodynamics, which he understood as the mean nonlinear electrodynamics, the laws of electrodynamics follow from the law of gravitation, which sounds outrageous. How could the laws of one field follow from the laws of another field? And in order to get a glimpse why this can be true, just consider the energy momentum tensor of Maxwell's theory and consider vacuum electrodynamics, just vacuum, because in order to compare to Mies' theory, you have to take the vacuum theory. And now, as we know from Einstein's equations, it follows as an integrability condition that the right-hand side of Einstein's equations must be covariant divergence free. So if you take the covariant divergence of the energy momentum tensor, just by elementary manipulations, you can show from the energy momentum expression that this is equal to that. And then you see that if the field is generic, that means if the determinant of the energy momentum tensor is non-zero, the field equations follow. And that can be repeated in very general terms. And that is, in fact, Hilbert's proof. Hilbert's proof is, let me skip this mathematical step and just give you the full details. You can actually have it on one screen full. You derive second Noether identities from the fact that the gravitational part of the action is diffeomorphism invariant, and the full action is diffeomorphism invariant. And that is actually quite independent of what the precise form of the Lagrangian is. The only thing you are using is that the action is diffeomorphism invariant. So for any diffeomorphism invariant action, that is true. And what you get is the sort of equivalent statement to what we had before. The variational derivative of the gravitational action with respect to G is divergence free. Then you also invoke a condition that is derived from gauge invariance of the electromagnetic field, of the electromagnetic potential. And then you get an equation from the diffeomorphism invariance of the full action. And now these three equations together contain Hilbert's theorem. Because if that is true, this term drops out. If this is true, the last term drops out. So only this term, the second term, and the third term survive. And now you see if the sorry, this should be yeah, if this is if this term drops out, then you see that if that is zero, if the equations for the matter are satisfied. Sorry, if the equations for the gravitational fields are satisfied, then the equations for the matter fields will be satisfied. And that is Hilbert's statement, that from the gravitational field equations, the field equations of matter follow. And he is very enthusiastic about this in his paper. And he says, we are almost holding sort of the unification of physics in our hands, because once GR is imposed and the notion of diffeomorphism invariance is imposed, we now understand what the equations of the matter will be. Okay, so I basically used up my time. Will I have 3, 5, or 4 more minutes? Is that okay? Or should I stop?
It's fine.
Here? It's fine? Okay. So Hermann Weyl was another mathematician who contributed endlessly to GR and with very deep insights. And he wrote this marvelous book called Raumzeit Materie in 1918. And I just want to mention the things he did. He develops the differential geometric background by separating the notion of a metric and the notion of a connection, which was important later on. He dramatically simplified calculation. His derivation of the Schwarzschild metric is half a page long, due to a trick that we can discuss later. He also found the Eisner-Nordström solution independent of Eisner or Nordström in the years between them. Eisner was first, then came Weyl, then came Nordström, but they all did it independently. He discussed the relevance of this solution for the construction of elementary particles. He introduced the notion of a Weyl space and a Weyl metric, which he used to give a new idea of how to unify electromagnetism and gravity. He defines for the first time the notion of what is a cosmological model. It's not only a space-time satisfying Einstein's equations, you also need a preferred foliation, perpendicular to time-like geodesic congruence. And he suggested an axiomatic basis for GR, which does not use rods and clocks, but light signals and so-called projective structures, namely unparametrized geodesics. So particles and light signals are the elementary concepts in GR. That's a technical detail I want to skip. And here are a few pictures from the de Sitter space. Weyl's idea was that you can get all geodesics on de Sitter space by cutting the hyperboloid in 5-dimensional Minkowski space by 2-dimensional planes, which go through the origin. The intersection of such planes with such an hyperboloid is automatically a geodesic. And now, if you apply the Lorentz group by sort of moving around the surface, this plane, you get more geodesics. And he recognized that these different ways of generating congruences of geodesics precisely correspond to the different ways to slice de Sitter space. And so you can slice de Sitter space in the static version, which in fact is by non-geodesics. This is the original version that de Sitter had. You can view de Sitter space as a family of closed spaces, contracting and expanding in time. You can also can view it as a monotonously expanding part of flat spaces. That's Weyl's preferred choice for various reasons. Or you can view it, or parts of the space, you can view it as an expanding series of open, that means negative curvature spaces, all of them in the same space-time. And that's something Weyl came very close to. Okay, let me stop now and read to you from a letter that Albert Einstein wrote to Felix Klein in 1917, discussing GR and its future fate. And he said the following: what you call agnostic regarding your point of view is also represented in mine in a twofold way. Whatever of nature's feature we may display according to the principles of simplicity, its theoretical treatment will never prove correct once and for all. For example, Newtonian theory seems to represent all of the gravitation field in a complete fashion through the scalar potential phi. But this description proves to be insufficient. It needs to be replaced by the functions g mu nu. I do not doubt that the day will come when this way of conceiving gravity will have to give way to another, which differs from it fundamentally for reasons that today we cannot even imagine. I believe that this process of deepening our theories has no limits. Okay, they are finished. Thank you for your patience. That's all.
Thank you for your very nice talk, Nico. Are there questions in the audience?
You can just ask anything.
I would suggest you simply unmute yourself and then ask questions. Yes, Maurice?
Yeah, thanks for your very detailed overview. I'm sure that took a while to prepare. I'm very curious, what did you learn along the way about Einstein's thoughts about inertia? Because after all, inertia is essentially removed by switching to geodesic motion.
Yes. What I learned is that the essential ideas that we have today actually came from Hermann Weyl. So I think it was Hermann Weyl who explicitly said that there is no such thing as a gravitational field. He says that there is an inertial structure, yeah, and that the inertial structures encodes what we used to call gravity. And he calls the field the Führungsfeld, the guiding field. So he identifies the guiding field with the differential geometric concept of a connection. And he said it is the connection that tells us how things must move if no forces act on them. And gravity is not part of the forces, it's part of the guiding field. That's literally what Hermann Weyl says. Einstein was less clear, in my opinion, about this. But Einstein praised Weyl's presentation of GR very much. He did not agree with Weyl's idea about unification with electromagnetism. He in fact was strongly against it. But the presentation of GR in Weyl's book was very much praised by Einstein. In particular, the separation between the metric aspect and the connection aspect. I don't know, does that answer your question?
Well, it depends what you study, right? If we look at modern cosmology, we have all these puzzles on scales, in particular less than a Hubble scale, where the question naturally arises: am I looking at something anomalous solved by dark matter, or the same anomaly solved by unusual inertia, and so on? To what extent does general relativity fulfill all the promises in cosmology? And you can be a bit more succinct about it. This is a related question, I think. Well, you can think of it as an hypothesis. To what extent does general relativity give a satisfactory answer to the true nature of the vacuum in cosmology?
Yeah, that's of course a difficult question.
I mean, that goes beyond Einstein's time, of course.
Yeah.
That has to be included.
So as I hinted at in the talk, Einstein initially had this strong idea about Mach's principle, which relates to cosmology, which you also find in Hermann Weyl's book, stronger in the first editions and less strong in the later editions, because it is difficult to formulate Mach's principle in field theoretic terms, because Mach had the idea, he stuck to the sort of ontology of bodies that you can see and that make up the cosmological background. So that inertia is really the interaction with moving bodies or ponderable matter, as they said at the time. Now, in present cosmology, we have these ideas that we can shift around the geometric aspect, that we can have, for example, we can add torsion to our theories, or we can add non-metricity. So we can have more general connections rather than just the Levi-Civita connection corresponding to a single metric. And I think this way of thinking about more general geometries was opened up by Hermann Weyl. But whether one can say that GR, in the way that Einstein conceived it, actually contributes to a solution to those problems, I mean, that takes a longer discussion, I think. A difficult question.
Yeah, I know. Thanks.
Yes. Sorry.
Yeah. No, I'm finished.
Okay, then Kama.
Can you hear me?
Yes.
Yes.
Okay, thanks
Hi.
a lot for the very nice talk. I have a question in order to not understanding incorrectly about the work by Hilbert, the submission and the revision. The
Yes.
question is, at the time of the revision, did he know about the correct equation of in the work of Einstein, or
Yes.
yeah.
Yes, because
Oh,
Einstein's
okay.
paper was published because before Hilbert resubmitted his.
Okay,
So
okay, great.
he certainly knew about it also because Einstein had close contact with Hilbert. They wrote letters to each other. And when Hilbert finally submitted his paper, then Hilbert, there was a very short period of misunderstanding. And Einstein then wrote a letter to Hilbert and said, well, you claim you had the equations first, but actually I explained my equations to you when I was in Göttingen. I think that's not quite fair, and so on. And then Hilbert completely conceded with this. And I don't think that Hilbert was trying to do anything wrong. It was just carelessness. They were careless in the printer's office and not, as we do today, properly acknowledge later changes to the paper.
Okay,
That's
great.
I think that's the
Great
whole
information. Nice.
Yeah.
Thanks.
Yes, Shen.
Hi, this is Shen. I happen to notice that in one of your notes, you wrote that Dyson tried to estimate the gravitons captured by the Earth in several million years and several solar gravitons.
Yes.
Can you elaborate that? Because as an astrophysicist, I, of course, are very interested in the detectability of these gravitons, kind of things.
Yes, well, I cannot reproduce the calculation. I mean, there's certainly certain assumptions going to this calculation, but he actually has a published paper on this. It's based on a talk that he gave at the University of Boston, I believe, but I'm not quite sure, in 2006. And I think the paper is called "Can We Detect Gravitons?" And if you Google this and you say Freeman Dyson, you will immediately find it. And it's actually a very nice paper. I do know that not all colleagues agree with his pessimistic calculation, and they also do not agree that even if his calculation is correct, that you should draw the conclusions that he draws, namely that sort of any attempt to speak about gravitons are physically basically irrelevant, right? He sort of hints at this conclusion. And that, of course, may be disputed. But it is what I wanted to say with this is that still today, eminent people argue that perhaps we should not so much think about very, very remote effects that a sort of quantization of the gravitational field might have, rather than some other problems, right? And yeah, I think I would refer you back to Freeman Dyson's paper. There is a long elaboration on his paper by some other people who redo all the calculations and basically found them correct. Yeah, if I had more time, I could post this in the chat.
Okay.
But I can write you an email.
Okay.
If you like.
I will
I can
also look that up myself.
Yeah. The other, try to remember the other names. I send it to Torben and he can distribute it, okay? It is a really interesting paper because, I mean, Freeman Dyson is a person of a huge experience in quantum field theory. I mean, he's not making lighthearted claims. So I think his argument is a strong one. And indeed, the question is whether the concept of graviton as we used it today is really a useful one. You see, if you open the booklet on the particle data group, where you see all the details, for example, you can look up the mass, upper bounds for the mass of the photon. And you can also look up the current upper bound for the mass of the graviton. And it's surprisingly low. It's much lower than the upper bound for the photon. And you might think, on what theoretical basis has this been estimated? Because you cannot estimate the mass of a particle unless you have some theory that describes the particle and makes some prediction against which you can test the observation. And it's very hard. And I used some years of my lifetime in trying to formulate a theory of massive gravitons. That's very difficult. And the theoretical basis is very poor, because the whole notion of a graviton, a photon, refers to Poincare invariance. It refers to spin and mass. And spin and mass are the Casimirs of the Poincare group. But in GR, you don't have a Poincare group. You do have a Poincare group if you have a Minkowski background about which you perturb. In this special circumstance, you have it. But fundamentally, you don't have it. And that is an issue. You have to, is the graviton only an approximate concept? Is that still valid in cosmology? And that's difficult. Okay, yeah.
Okay, thanks.
Are there any other questions? If not, maybe we can end the official part of the seminar here and make some kind of open discussion for those who are interested. So thank you very much again, Nico, for your nice talk.
So I just stay in line and for some minutes, and if there's some more questions, I'm happy to answer anything I can answer.
Yes.